Hello, Romania. Hello, everyone here. Very warm welcome to today's session on cycling the drain, trends into wastewater, water reuse, and circular economy. My name is Enkeleida Ginali. I'm 31 years professor at Polytechnic University of Tirana. Joining me as a co-moderator is engineer Elsa Belba, representing young water professionals in Albania and currently working as at the Agency of Water Supply and Sewerage in Albania, the most specialized institution in our country. We both are sincerely honored, delighted, excited to be here today as moderator of this fantastic and extremely informative session, which has been superbly organized by Kati. Big thank you to Kati for her tireless and insightful work. On this journey, I would like to bring apart from yourself, without asking the organizer, a good friend, a stakeholder who is always absent when we deal with the negotiation on environmental issues, a stakeholder who refuses to compromise planet Earth. The trouble is that we are putting a quadruple squeeze on this poor planet. Population worldwide will nearly double by 2050, so more wastewater, more pollution. Climate change will intensify challenges for water demand and consequently wastewater and pollution. Today, we are putting and using nature 1.7 times more and faster than the planet Earth can regenerate its ecosystem, coming from this big size to this size on what we call raw material. The fourth pressure is a surprise. We need to abandon our old paradigm, take, make, and dispose, and shift it to circular economy in a transformative framework. Colleagues, let's leave the old paradigm behind. Therefore, today, together, we'll explore the latest trends in wastewater treatment, emerging practices in water use, and how this fits into a broader concept as circular economy. These themes are essential as we seek to treat and transform our linear consumption and waste pattern into regenerative systems that such both of our resources and good ecological status remain as such. In the first part of our session, we are fortunate to have with us esteemed speakers, starting with Ana Delgado, World Bank. She will introduce a new approach, a fresh framework that extends beyond reusing and recovery resources from wastewater. This innovative perspective aims to enhance the financial and environmental sustainability of the wastewater sector while enhancing resilience and mitigation emissions. Inspired by the circularity of water in nature, our esteemed speakers, Ms. Lindita Shakiri and Ms. Alenka Zelaznik, will guide us in reimagining the water cycle from large to small-scale wastewater treatment plants. Their insight will focus on delivering resilient wastewater and treatment services while preserving and regenerating natural systems. They'll also highlight the valuable approach of incorporating natural-based solution. Thank you. Anna, she's online. Floor is yours.
Okay. Thank you so much for the introduction. And thank you for allowing me to connect remotely. I'm sad I cannot be there. Okay, can you see it well? Yeah, right? Yeah. Okay, so good morning, everybody. My name is Ana Delgado. and I will be focusing my presentation on the framework that we developed at the bank, that it's called Water and Circular Economy and Resilience Framework. And I think, yeah, the challenges I have been just told right now, and we know them, that there's increasing demand for water, increasing pollution, while at the same time, water is undervalued and the level of service is insufficient. And we have also climate change, which is having an impact on our natural resources. I wanted to include here some of the conclusions of a very recent World Bank report publication that it focusing on like the challenges that we have in funding and financing the water sector. And I wanted to put here 4 of the key issues they found. One is that we're not investing enough in water to achieve the Sustainable Development Goals. 2 is that most of the spending in water comes from the public sector, as I think we all know that. But surprisingly, despite the large funding gap, the water sector is not able to spend all the allocated budget that they have, which this was surprising. And only 35% of the utilities assessed fully cover their operation and maintenance costs. So can circular approaches help with these challenges? Can we create new revenue streams, create new opportunities for new business models? Can we help attract the private sector, create a path for financing from other sectors? And also can it help improve the efficiency of the utilities? And I hope by the end of this presentation and these sessions here that we all agree that, yeah, circular approaches can indeed help. But first of all, I want to introduce a little bit circular economy. I don't know if you're all very familiar with it, but circular economy emerged as a response to the current unsustainable linear model of take finite resources, make, consume, waste, and pollute, which is really unsustainable. And there are several definitions of circular economy, but I think the most used is the one by the Ellen MacArthur Foundation, which is based on 3 key principles. One is the regeneration of natural systems. 2, we need to design our waste and pollution. And 3, we need to keep products and materials in use. I wanted to emphasize that circular economy is not a synonym of only recycling and reusing. It goes really way beyond that, and we need to start thinking of different ways how we create different processes so that circular models really can build not only economic but also natural and social capital. I think, yeah, circular economy is still mainly applied in other sectors, I think mostly manufacturing and fashion, but thankfully more and more publications and institutions are addressing the relationship between water and circular economy. Here I've put some of the early publications that came up that assessed this relationship, and these publications also informed our WISER framework, especially what you see in the middle that are the R's of reduce, reuse, restore, and recover. Here, well, sorry, there's a lot of text, but I wanted to put this slide to highlight that the principles of circular economy are also in line with the climate goals and also offer opportunity for climate mitigation and adaptation. Here, well, I've put here a lot of examples, but one of them is reducing non-revenue water, which improves resource efficiency, also help reduce energy needs and therefore greenhouse gas emissions. So circular economy, we believe, needs to be applied also in the water sector. We can be inspired by the circularity of water in nature. And we think that we need to include 2 important key issues: resilience, and also we need to be inclusive. So as it's been said also before, we need to shift from the current linear system that we have in most of the places in the world to one that is circular. And here you can see the water and circular economy and resilient framework that we developed. And the purpose for us, as we were having more and more demand from countries to implement those principles, was to have our own common understanding of how can the circular principles can be applied in the water sector, and to have a clear framework when we're supporting the countries implement those principles. So in the outer green layer, you can see the three main outcomes that we want to achieve, which is deliver resilient and inclusive services, design out waste and pollution, and preserve and regenerate the natural systems. And then in the inner darker blue layer, there are the 9 actions that we think are needed to achieve those outcomes. And I will talk about it in the next slides. And all the actions are also described in detail in our report, which are linked in this QR, but you can also find it in our website that I'll show at the end. So the first requisite for us is to value and use to its fullest potential what we already have. This should be like a key principle of circular economy. The existing infrastructure that we have can be retrofitted or optimized to increase treatment capacity, to provide additional services, or to maximize service delivery at a fraction of the cost of new infrastructure. I have included here a table from a very interesting case in Sao Paulo, also with some support from the World Bank. The utility, instead of investing in tertiary treatment to meet the new quality standards, they were able to optimize the existing treatment processes individually to increase treatment capacity and quality levels. And this resulted in huge savings for the utility. Then key to circular economy are also operations optimized for efficiency, reliability, and performance. It makes no sense, especially in many of the countries we're working, to start reusing, spend a lot of money and start reusing wastewater if we're losing most of it through the pipe. So reducing non-revenue water should be one of the key issues if we want to become circular. We also need to diversify water supply sources, including in the portfolio sources with different risk and cost profiles, and with low vulnerability to shocks and stresses. That way we can also hedge against risks such as climate risks. And of course, reuse of wastewater and other unconventional sources must be part of this water balance. Resources can be recovered over the entire water cycle in the form of water, energy, nutrients, and other materials. And ideally, all these recovered resources can provide an additional revenue stream for the utility or to reduce operations and maintenance costs. That way we can help the utility to become more financially and environmentally sustainable. And resource recovery, as I guess we will see later, it can be done at different scales and may include centralized and decentralized solutions. And the right solution really needs to depend on the local context. Because energy is often the costliest component of water supply and sanitation operating cost, energy efficiency and renewable energy serve both to reduce emissions and also to strengthen the financial performance of the utility. And when we talk about circularity in water, many people think about biogas, but I think we need to think beyond that, beyond using biogas. I have included here some examples of solar, but there are many more utilities exploring solar or wind to reduce their climate footprint and to reduce energy costs. One key issue of becoming circular is also to proactively preserve and regenerate natural systems. For example, we can use non-nature-based solutions such as constructed wetlands as part of the wastewater treatment. And it is also crucial to manage and recharge our precious aquifers that can also help us adapt to climate change. Here, I also wanted to include that, of course, there's always key cross-cutting issues that are important factors in the successful adoption of becoming circular. For example, it's very important to manage water demand and decrease water use where possible and become more water efficient. We need to create the right policy, institutional, and regulatory environment to be able to promote those type of solutions. Or stakeholder engagement is also key in order to ensure social acceptability, especially when we're talking about reuse. We believe that implementing circular economy principles also makes economic and financial sense, because as I've mentioned before, and we've documented through our projects and other case studies, we can create additional revenue streams, we can reduce operation and maintenance costs, which then offer a better return on investment. This also can help bring or create innovative business models and bring the private sector to manage those new businesses. And there's also potential to tap into other sectors' financing, such as green or climate bonds, if we're recovering biogas, for example, and using biogas, or environmental impact bonds when we talk about nature-based solutions. So how are we implementing this wiser approach at the World Bank? We're promoting circular economy principles through policy dialogues in different countries, creating new policies or new regulations that are needed to go towards circularity. We're also supporting governments to implement circular economy principles in water projects. For example, under the Tamil Nadu Sustainable Urban Development Project, the World Bank supported Chennai in designing and financing a tertiary treatment plan to treat wastewater and then sell it to industrial end users. And with these additional revenues, the utility can cover operating and maintaining costs of this part of the project. So the capital investment in the reuse project was recovered in 5 years. And we're also helping this utility implement other circular economy activities. For example, the utility has retrofitted 7 of its wastewater treatment plants to recover energy from wastewater and to supply more than 50% of the energy needs of the plants. And these are also other examples of projects that have circular economy components, and we are receiving more and more requests to implement circular economy principles in water. As part of our initiative, we're also documenting relevant case studies from around the world, which you can find in the websites showed here. And these case studies have also informed the development of our framework. Here, quickly, I wanted to show some of the lessons learned from these case studies that we have documented. So one, stakeholder engagement is very important from early in the process to be able to identify the end users of these recovered resources and to ensure social acceptability, especially when we're talking about reuse. In the case studies, either there was a very clear regulatory framework, or if not, the roles of the stakeholders was really clarified via the contracts in the project. So that's very important. And when there's lack of regulation, it can be solved through the contracts. In the successful case studies, also they leverage the resources recovered to create additional revenue streams, and that way they would make the investment financially sustainable. And finally, at the same time, there always needs to be parallel investment to improve the efficiency of operations or any of the utility in general. We're also developing workshops where countries that are embarking in circular solutions can share their challenges and opportunities and lessons learned. And finally, we're also developing tools and frameworks. For example, recently we developed an online quick assessment Wiser tool that you can check either using the QR showed here or wiser-tool.com. This assessment tool is very simple, but we've found that it's very useful to use in stakeholder workshops to familiarize the user with circularity in water. Maybe they can assess if one of their projects is really circular. And the tool also presents solutions, guidelines, and other resources. So we think it's very easy to use, and it has worked quite well. It's very visual, like color-coded. And it really helps the user understand what do we mean when we talk about circularity in water. So I suggest you should check it out. I wanted to finish with some key takeaways from this presentation that I think it's clear that water circularity goes beyond reusing and recovering resources from wastewater. It requires a more holistic approach for water and sanitation services, because it also needs to include restoring and enhancing ecosystems, considering the water basin. It needs to include resiliency principles and also climate mitigation and adaptation strategies. Two is that implementing circular economy principles can also make economic and financial sense if they're designed correctly. Three is that water circularity should not be the end in itself, but the means to achieve higher outcomes, which that in ultimately what we want is universal and sustainable access to water services. And four is that cross-cutting interventions such as demand management or the enabling policies and regulations and also stakeholder engagement is crucial to move towards circular approaches. And yeah, here I just have the link to our website where you can find the Water and Circular Economy and Resilience Framework report, other reports that are related to this issue, and all the case studies and tools. And my email is there. If you have any question, you can always reach out. Thank you so much.
Thank you, Ana. World Bank is proposing WISER. In fact, is a framework. And this framework is to guide practitioners who are incorporating principles in policies and strategies, planning, investments, design, operations. So to be honest, what we need now are followers. So over to you, Elsa.
Thank you. We are privileged today to have with us a distinguished female engineer, Ms. Lindita Shakiri, with 27 years of experience, first as technical engineer at utilities in Skopje, and today working as a project advisor in the Ministry of Environment and Physical Planning in North Macedonia. Ms. Shakiri, the floor is yours.
Thank you very much, Elsa. Thank you very much, Keida. Thank you to organizers. Thanks to organizers, IAVD, for inviting us, for organizing such event where we can share experience, good practices, share new ideas, and of course, to get on board some other followers and young professionals. Thank you for the introduction. It's a little bit difficult after yesterday party to be ready for science, new science idea, but however, I think that we will understand each other. I will present our project. I was in the public enterprise water supply and sewage in Skopje. I was head of project implementation unit for implementation of the project, which we are proud with. It is a wastewater treatment plant in Skopje, the hugest environmental project in our country. It is really amazing that we started, Vodovod and Kanalizacija started as a promoter from 2017 to deal with these projects. And now I'm happy to announce that this summer we will have access to the site, which means that we will start with real implementation works on the site. So in my presentation, I will present first the introduction, main characteristic of the plant. I will be focused on energy consumption. So and how we are using at the end, how we are using the ash of the sludge, since with our incinerator that we are required from the constructor, we will let's say deal with the burning issue, and that is disposal of the sludge. So we will incinerate the sludge. Okay, start from the beginning. So the project, as I said at the beginning, it is very important for our country. It is in the all pipelines as high priorities of the government. So it is supported by many stakeholders. The Ministry of Finance, Ministry of Environment, City of Skopje, and as the owner of the utility of public enterprise, which will implement the project and which is promoter of the project. So during the implementation, we will implement the urban wastewater treatment directives, which is very challenging for us, since those are EU directives, and we hope it will help us in approximation of the EU standards, and as well as EU as Macedonia as a candidate country soon will become a member country. The project is financed by EIB, EBRD, and WBIF grant. So this is a loan which is granted by the Macedonian government, and the EIB as a leading IFI, they covered or they supplied 68 million euros, EBRD 58, and we are very happy that EU recognized this project as a really very environmental important for a region. So we received a grant from almost 70 million euros, which are appreciated amount of money in all our region. So this is the length of the site. So the main characteristics of the site, it is in the municipality of Gazibaba on the left side of the river Vardar, and it will cover the wastewaters from all the city, except from the one municipality of George Petrov, where already exists one wastewater treatment plant, Volkovo. So the long-term projects for this wastewater treatment plant is 650,000 people equivalent, which is, speaking with Keida, it's really very demanding. Yes, it is a fantastic. I hope so that we will meet these requirements. So going further, so those are the main characteristic of the plan. So the horizon is 2045. So it's for 650,000 people equivalent. So we have preliminary treatment, primary treatment, secondary treatment, and at the end, sludge treatment in the incinerator. So what are the objectives which should be required? So what is very important, our wastewater treatment plant is designed to work in regimes, which means 33% at the beginning. So to be honest, we do not have total load now. And at the end, to be covered 100% of the designed loads. I want to mention that before constructing of the wastewater treatment plant, City of Skopje, public enterprise, did two amazing jobs. So they were financed or granted by EBRD. So we did inflow infiltration study. While performing for 1 year inflow infiltration study, we really gained very interesting figures. And what is required after that in the loan agreement with the banks is that City of Skopje or Public Enterprise Vodovod and Kanalizacija should implement the priorities of this inflow infiltration study, which means that in the future, or while the wastewater treatment plant will be building, the City of Skopje should cover should work on a recovery of their sewage system, since we have a lot of infiltration, so there is a high dilution of water which should be treated. So which are the requirements? The requirements are treatment efficiency of BOD, the concentration of BOD to be 25 milligram per liters, and treatment efficiency to be 70 till 90%. COD, treatment efficiency to be almost 75%. But for long-term objectives, we are planning as well to go on the tertiary treatment. So it's removal of nitrogen and phosphor, almost 70 to 80%, which is high number to be set, but I really believe in the company which will construct the wastewater treatment plant, so we will meet the objectives. Speaking about the numbers and the figures, I want to mention that those are already projected numbers. So we are still in the phase of implementation. We will see, so we will have 3 years construction and plus 2 years defect notification period. We are happy to say it's always it's 1 year, but we are yes, our efforts, and we succeeded to gain 2 years. And so we will see what we will set, and are those meeting objectives will be met. But once again, I hope that we will do it. So now a little bit focused on the sustainability of the wastewater treatment plant, which we as promoters, we are really very proud. So at the end, you will see that the wastewater treatment plant Skopje is planned to be 100% sustainable, which means it will circle its own energy for using the energy. So we'll produce the energy, to use the energy, and at the end to treat the sludge. Okay, so we will have 3 sources for energy. So it's combined heat power biogas utilization, and it will produce per year almost 10 million kilowatt hours per year. Steam generation, which will produce almost 800 kilowatt hours, and solar, I will skip this. And solar panels, which are on the length of almost 9,000 meters squares. So they will produce 3.2 million approximately kilowatt hours per year. And speaking about summer energy production, if we account the production of the heating power is 10.671 million, production of steam turbine is 3.1 million, and production of solar plant are 762,000 kilowatt hours per year. In total, it is almost 40 million kilowatt hours per year. But Skopje wastewater treatment plant the demand is almost 10 million kilowatt hours per year, which means that Skopje will not be just a treatment plant for a wastewater, it will be a green energy power plant. Coming in the end, I want to mention that incinerator is a really unique one in our region, which means that at the beginning, since there will not be so much sludge to be treated, it could be a regional incinerator. So there are another source for receiving funds for public utility. I think that we will working a little bit in a law for environment in a way of transport of sludge, so we can become a regional center for incinerating of a sludge. What is very important, we can, at the end, the ash of the sludge is not throwing on the land, but it is using as well. So it can be used in the construction materials as a cement and concrete production. It can be used in the road construction at asphalt and road base. It can be used as a soil amendment and fertilizer. In the end, it can be used as a metal recovery. So we will use the ash. We will not throw it, even the sludge, we will not throw it in the land. So we will have really sustainable energy, very efficient wastewater plant, which is very innovative, high-tech, green asset. And at the end, I want to thank a lot, first, to the government which succeed to gain the loan, to the banks who are very supportive during all the process, to WBIF and to EU for getting us the grant. I want to thank a lot to the young professionals as my team in PIU, who are very enthusiastic, very supportive. Many of them during the process have their master thesis on the wastewater treatment plant, which is really amazing. I'm proud of them. So thank you, thanks to all stakeholders. Even sometimes we have difficulties during negotiations and coordinations, but I believe that we will receive really a good project. Thank you.
Thank you very much. It's a big congratulation for North Macedonia, who has carefully treasured the past experience of wastewater treatment plant. Based on that, they have started to think big and bold, to go for a wastewater treatment plant, which is going to be served to 650,000 population equivalent, the largest wastewater treatment plant dared in the Balkan region. And they have decided to turn the wastewater treatment plant, the waste to be treated, into several production. They'll dare produce energy from 3 different sources. They'll dare to treat sludge and to use it in the agriculture. They'll use ash as well in the agriculture. And they'll produce culture for us, the others, to follow. In the same time, the best, the cross-cutting with university, with research, and at least with young water professionals. Really thank you, and big applaud for North Macedonia.
We are privileged to have with us in our session a distinguished speaker, Ms. Alenka Zalaznik, who serves as a project manager for applied ecology at Limnos company in Slovenia. with a portfolio encompassing 200 constructed wetlands for treatment of domestic sewage, industrial wastewaters, and landfill leachate and sewage sludge from wastewater treatment plants. In parallel, she holds the position of Deputy President at the Global Water Partnership of Slovenia. Great to have you, Ms. Zelansky. The floor is yours.
Thank you very much, ladies. Good morning, Romania. It's very nice to be here. Thank you for the organizers to give the floor also not just to high tech, but also to low tech. I would like to focus in my presentation. I would like you to focus on my presentation through certain lenses. I would like you to pay attention to the multiple solutions that can be formed and implemented through nature-based solutions. Also, bear in mind that these are low or no energy consumption. They are enhancing biodiversity. We haven't heard much about biodiversity, but this is the part of the day when this aspect is quite important. Also, I would like you to focus on the local resources used, not just resource efficiency in terms of of treated water and sludge, etc., but also the way how these solutions are implemented. So they are implemented using local resources like gravel, local plants, and also local constructed companies, because these are mainly groundwork. So they're very simple to install. They are interdisciplinary also in our company. I come from Slovenia, and we employ hydrologists and biologists working together to produce solutions like this. I will be focusing on wastewater treatment. I will mention some leachate treatment and also stormwater management, because these are most common solutions used using nature-based solutions. Starting with the constructed wetlands, they were mentioned today already in this presentation. For all those who do not know the procedure, the constructed wetland for wastewater treatment is a simple operation. So the sludge coming from, for example, a village is collected in the sedimentation tank and then runs through the substrate, through different forms of gravel, through roots of the plants, and in the end, it will exit from the system purified. So we use substrate. They are meant as a filtration, absorption of pollutants. We are using substrate, it means a base for plants that we are planting, and is a surface for microorganisms. The microorganisms are, like in conventional treatment, wastewater treatment plants, a main source of treatment. Yeah. And plants, they can be different varieties, usually used the local varieties, and there are the area for microorganisms, and they also induce additional oxygen to speed up the process. The solution is useful for the entire villages. This is one example for a village of 500 population units, or up to almost 2,000 population units. Of course, also bigger if the area is available. So this is an area-intensive technology. In Slovenia, we use this technology also for certain pollution sources, individual, like mountain cabins, like this is a case from a petrol pumping station, or scouts camps, or many individual houses, those who are not within the agglomeration. I will say a little bit more about our biggest constructed wetland in the region that we have prepared a technology design for, and it's placed in Croatia, in Kaštelir. The reason why this technology was suggested is because there was sufficient area. You can see that you can barely see that there is a wastewater treatment plant within this nice agricultural landscape. And the variation of the population increases a lot because this is a tourist area, and during the summer there is almost 2,000 people here, but during the winter it's more than half less. So this fluctuation in pollutants poses no problem for these natural systems. The system is in operation since 2016, and it's consisted of 5 beds or basins. And the water flows both vertically and horizontally through the system. So this is a mixed technology system. And also sludge drying reed bed is added to the system, I will say a little bit more later. What I would like to say is, since we have this experience of operating such a system, we work closely with the operator on other costs. So the yearly cost of operation of such a system is like 3,600 euros per year, and these are mostly workers that attend to the constructed wetland every week. So they come and inspect every week. They will they will harvest the plants during the winter, because this is a naturally a necessary job to do. They will use a little bit of energy to install sludge onto the sludge drying reed bed, and there is also some telephone data, because they have this system in place wherever there is the data is available for them. Also for the user, this is a very cost-efficient system. So their wastewater treatment is in line with the regulation, and it costs 0.6 euro per cubic meter of sludge, of sewage water. On resource efficiency, I would like to point out that water reuse started in 2022. You know, there was a huge drought in the region. Wastewater treatment plant is, so there are vines and there are orchards around. So this water was already suitable to reuse directly from the collecting tank. And also the sludge reuse is a part of the system. So this is a resource efficient place. The resource loop is present. So all the sludge is collected in the sludge drying reed bed. This is a little bit different than a constructed wetland, but it's placed also here. It's just one small reed bed. Initially, there were 3 planned, but only one was realized because it's a Mediterranean climate, and it works really well also with just one. In the end, we hope when the sludge drying reed bed will be filled, we hope that this material will be reused in agriculture. If not, other resource efficient solutions will be found. And also I have mentioned that biomass harvested every year. This is a necessary process, and this is reused in agriculture also after it is composted. Treatment wetlands in the Western Balkan region, as far as we can gather, they are increasingly in demand. For example, in Croatia, there is currently a lot of sludge drying reed beds being placed along the conventional methods of wastewater treatment. This will enable the country to actually think about sludge reuse strategy in the following years. It will buy them at least 10 or more years of time. But these sludge drying reed beds are reusable even after this first filling and reusing the material will be done. Also in Montenegro, there are several locations you can see where either a constructed wetland or sludge drying reed bed or leachate treatment is performed during nature-based, using nature-based solutions, because they have many protected areas. These locations are next to the rivers, next to the lakes. And this is why the decision to use this technology was decided. There are also some locations in Northern Macedonia, so not just the Skopje, but also some small points that we're happy with. This is a combination of a constructed wetland and sludge drying reed beds. So we are tackling all the pollution sources on one spot. And even in Kosovo, the things are moving well. This is the first constructed wetland from Kosovo. It's not from our design, but I'm mentioning it nevertheless. So it's a known technology. The nature-based solutions are quite flexible, and there is many solutions available. There's quite a lot of information about that on the internet. I'm pointing out one latest website where they can present all the different solutions according to the pollution load, according to the surface that you have, according to the availability of area, geography, pollution loads. So the solutions can really vary, but you need in the end a skilled designer to design the solutions, because the devil really is in the details, like in any case. So we can have really different open areas, closed areas, a French system where combining sludge and wastewater treatment in one basin, etc. I'm mentioning also the zero leachate treatment. This will consume a lot of area, but nevertheless, it will enable the business model of charging the treatment of wastewater and also producing biomass. This is a solution quite known in Scandinavia and other developing countries like India, for example. This is a case I would like to present also from Slovenia. We started like 30 years ago, and this was one of the first locations of the wastewater treatment for a village of a population of 250 initially. But during the years, population grew. This became a protected area. There is a tourist camp. There were floods last year in Slovenia. We were quite affected. So this needs for the reconstruction of the constructed wetlands. The area, the part of the gravel and the plants will be reused. And in order to ensure increased efficiency, we will turn this horizontal flow constructed wetlands into a combined lagoon type constructed wetlands. And we will be adding the sludge drying reed bed also to ensure this resource loop on one location. And there is a Natura 2000 site right next to this. So this will be, so this increased efficiency will also be observed. So we are managing not just purification and treatment, but also protection of the environment and biodiversity support. Stormwater management. Some parts of the process of wastewater treatment in constructed wetlands can also be used in other locations and for other purposes, like stormwater management. This is a case of rain gardens in Ljubljana. So urban areas are particularly affected because of the climate change. There will be a lot of heavy rains during the summer, and all this water has to be managed in a way. A rain garden is a natural like a basin, vertical filter, and plants will be used to support the biodiversity and also to retain water during the summer to cool the area, etc. This the case that we are working on. There will be two rain gardens. One will be for purifying the water from a parking nearby, and the other will be to retain and detain and purify stormwater from the roof. And there is another interesting case which affects, which stems from the urbanization. There will be a new investor decided to build a new compound of 30 houses close to the Natura 2000 protected area. So there was this demand that the stormwater is collected and treated before it's released into the Natura 2000 area. So what we will do is to use this part of the channel, make it a two-stage drainage ditch, empowered with plants, and then here we will do the detention basin, replacing the wet meadow. So this is a mitigation meadow for the lost habitat. And there will be another small pond, retention basin for habitat creation. And before the water will be released into the Natura 2000 area, here we will do the filtration treatment that the water will seep through and purify. It will be purified finally for being released into the nature. The stormwater management in industrial park, this is also one exciting case. You have heard today already about the polluter pay principle. This is the stormwater retention, which is, and it's polluted because of the waste processing industry directly on the brink of this industrial park that is close to the Natura site 2000. So what we will do is we will make this stormwater retention basin an open constructed wetland, and the water will come through here, will run below the floating islands as first part of the process, will run through the part with the heavy plants here, and it will finally seep through the filtration basin and into the Natura 2000 area. We can also treat landfill leachate with plants using this stormwater, using the treatment islands. So finally, I think that the key messages that I would like to give is that the nature-based solutions are flexible. They can be installed locally. They can address different pollution sources, and they can be also managed locally. Thank you very much for your attention, and I remain for any questions.
Fantastic. How I can summarize this parade of great examples on wastewater treatment plants, not only for wastewater, but even for stormwater, for leachate, which comes from waste, and stormwater as well, and Natura 2000, and a lot of reminding ourselves of so many constraints and requirements that we have from European Union. But these are absolutely great examples for countries like Montenegro, North Macedonia, Kosovo, Albania, Bosnia-Herzegovina, Serbia, with population ranging from approximately 600,000 to 6.6 million inhabitants. As we heard in the morning, Michel from DG Environment, we all know that after 30 years, the Council of Europe, they have reached an agreement on recast of urban wastewater treatment plant. This agreement mandates the application of secondary treatment of all agglomeration of 1,000 population equivalent and above. So I would like really to invite now all of you for the question and answer session. So who would like to address the question to our wonderful speakers, and they end up to be females? If not, I'll challenge my old friend Linda with a question. What challenges and obstacles did you face during the implementation of your project?
Thank you, Keida. There are a lot of challenges. First of all, there are many stakeholders. At the beginning, there was all the ministry, of course, 2 banks, EU delegation, French Treasury, which has funded the feasibility study for wastewater treatment plant Skopje. So many of them to manage and to be on the table, it is really difficult. Having in mind Balkan mentality and our habits. So it was really challenging. And that's why I'm saying at the end, I'm happy that we are now at the beginning of constructing of the wastewater treatment plant. So even during the negotiations, so where there was a period of the negotiations of the loans with the banks. So they are very demanding, of course, for their money. They want high requirements. From the other side, the promoters, the country wants the best, but they have to receive the money. So it is very challenging, and it needs a lot of efforts to handle, but we did it.
Thank you. And with further ado, I would like really to start the second part of this session. We are privileged to hear from our distinguished speakers who will dive into more advanced stages of wastewater treatment. First, Mr. Simon will introduce us the quaternary water treatment. We are absolutely familiar with first, second, secondary, tertiary, and now we are going to be asked to have a quaternary treatment. So be prepared, guys. Next distinguished speaker is Mr. Erwin Moos, who will share an extremely good example and case of water use of Madinati wastewater treatment plant in Egypt. So welcome to balance the gender here. We need it. He'll present the application of advanced biological treatment, followed by tertiary filtration and disinfection, and how the reclaimed water is pumped into a dedicated service network for urban irrigation purposes. Keep in mind, urban irrigation purpose. We'll conclude this tremendous informative session with Dr. Lucas Eagle, Project Officer of Joint Research Center in Spain, to provide the latest updates and future policy development concerning hugely important topic, and this is sewage sludge management. Thank you. Ilse, over to you.
We are fortunate to have with us esteemed speaker, Ms. Simon Bitterwolf, an environment engineer from the Swiss Water Association. Mr. Bitterwolf will guide us through the fourth stage of the wastewater treatment process. Without further ado, Mr. Simon, the floor is yours.
Thank you very much. Hello and welcome from Lausanne, the French-speaking part of Switzerland, and also welcome back to HITEC. I want to share with you the Swiss experience in reducing micropollutants in wastewater. But first, have a look back. Looking back, it's merely 60 years ago when there were only about 14% of the Swiss population connected to a centralized wastewater treatment. Nowadays, it is regarded complete, like except for some very remote places in the mountains that sum up of these 3% that are still missing here. And that can not only be seen like in graphs and figures, but of course, first and foremost on the rivers and lakes. Like in these photos that you can see here, and they are taken exactly at the same place with a time distance of about 50 years. Where there has been obvious water pollution, like foam on many waters and even swimming restrictions, today they can be used and they are crowded with people enjoying good water quality. In the same time, the development of wastewater treatment has been constantly and really fast. First, there was only a mechanical treatment that is not even displayed here in my time span. And in 1917, the first biological wastewater treatment plant was built for carbon elimination. That is like the first step here. Later came the elimination of phosphorus and nitrogen. This, by the way, is where Switzerland still lags far behind its European neighbors. That is a little side note as an example that not everything is perfect in Switzerland. So a few years ago or decades, one may have thought that by the time now, the waters will be clean already. Well, that was before we knew about micropollutants. These are residues of pharmaceuticals, chemicals, and so on, and they are not sufficiently treated so far, and they have a proven negative impact on water ecology. With these micropollutants, the situation is as followed. Here's an example of diclofenac. This is a painkiller that you may know from creams that you can apply or pills that you can take. And this is one of the substances that is found most harming to ecosystems in rivers. Displayed here is the concentration on the vertical axis of diclofenac in the river of Rhone over the last years, here on the horizontal axis. There's a threshold of 0.05 microgram per liter in the Water Protection Act, that is the official law in Switzerland. And at first sight, we can see that all values lay below this threshold. The axis actually stops at 0.03. But let's have a look at some more rivers. Be careful now, the vertical axis is different now on every of the charts, and I've displayed the chart I just showed you before here on the upper row. And we can see in these 19 rivers that some of them, I've marked the threshold of 0.05 in red, will exceed the threshold. So we have a contamination that is harmful for the environment. And we can also see that in some places, they even touch this dark red area that is in the lowest row here. And that means that in these rivers, we exceed the threshold by a factor of 10. And this pollution with micropollutants like diclofenac shown here is mostly originating from wastewater treatment plant. The limit values exceed depending on the flow rate and the share of cleaned wastewater in the rivers. So usually when there's a bigger river, we have less of a problem. In the smaller rivers, we have a bigger of a problem. But all in all, we have to say that we still have got a problem here. What has been done so far to solve this problem? First, strategical planning for the elimination of micropollutants has been done in 2006, here on the time span. And in a long process that I will not tell you in detail now, that has led to an adoption of the Water Protection Law in 2016, here on the right. So it has been a 10-year process involving many stakeholders like public operators, authorities, engineers, and of course, there had to be done a lot of research. So what does this Water Protection Act from 2016 actually say? It says that until 2040, about 130 of a total of 700 treatment plants in Switzerland must reduce micropollutants in their wastewater by a factor of 80%. Because these are mostly the bigger plants, we can by that reach a population of 70% of Switzerland. The criteria by which the plants are chosen are, like first criteria, plants with more than 80,000 inhabitants. By this, we can already reach a big proportion of the population and we have a huge load reduction. The second criteria is the quality control for drinking water resources. So we do choose plants that discharge into lakes or in special hydrogeological situations. And the last criteria is the protection of sensitive water bodies, and that applies to smaller plants that contribute more than 10% of water to the river they discharge. And these are mostly the red area parts that you saw on the previous slide. If we succeed in the treatment, we assess by the measurement of 12 so-called leading substances that you can see here on the left, and they have been carefully chosen by the criteria on the right side here. Most of them are pharmaceuticals, maybe you know some of them, because they can be found in almost all wastewater in sufficient concentration so that we can prove that we can treat them. And by the way, like the studies that have been done on these leading substances have proven very well. So the European Union will probably use the same substances in a very similar approach to assess the effectiveness of the wastewater treatment. The costs for this upgrade are pretty high. There's about 1.2 billion euro. So how does the funding work? These 1.2 billion euro, they have to be paid by the polluters, and that are the wastewater treatment plants, wastewater treatment plant A, B, and C. So at the end, all of us, the citizens, because all these wastewater treatment plants, they have to pay 10 euro per person in year to a fund. And out of this fund, we will pay back to the upgrade investment costs of certain treatment plants. By the way, this 10 euro per person in year equals half a pizza margarita in Switzerland, but by this half pizza, we probably won't even be sated. Once a treatment plant has finished its upgrade, then it does not have to pay this 10 euro per person and year anymore, but they have to pay the operational cost of the treatment. And this is also more or less 10 euro, as we have learned in the last years. So if the wastewater treatment plant gets the operation cost below 10 euro per person and year, then they can actually save some money, and the other wastewater treatment plants still have to pay this 10 euro. Now, a brief excursion into process engineering. How do we even treat the micropollutants in wastewater? At the beginning, like in 2016, there was almost no experience with the processes. So there were some studies, we had some pilot tests, and some plants, of course, they had to be the first movers, had to try some processes that we learned from and then could apply on the future projects. Meanwhile, 3 main processes have been established that are ozonation, activated carbon, either with powder activated carbon or granular activated carbon, or there's a combination of those processes. Which process is best depends on the individual treatment plant. And usually we decide this in a pre-study, taking into consideration many aspects. Not the last are the catchment area and the recipient, like river or lake. And the decisions are usually made in collaboration with operators of the plants, the authorities, engineers, and research. And there's us, the Swiss Water Association, who tries to link like all these stakeholders. At the moment, we have already 23 plants in operation with removal of micropollutants, and there are many more in planning or even already under construction. All of them you can see on this small map here in the colored dots, each of the dots representing, each of the color representing a different process. And the many more black dots that you can see are the rest of the plants that are not upgraded yet. So far that you can see in this graph, 9 plants run with an ozonation, 9 plants run with a powder activated carbon, and then there's some process combinations and some granular activated carbon. Whereas like in the last years, it has been a development towards more granular activated carbon instead of powder activated carbon that is not displayed here yet. On the right figure, you can see that the share of connected people to one of these processes is that we have more people connected to ozonation because this process is usually used on the bigger plants. Now, the final question is this upgrade enough to avoid pollution of the rivers? We're now coming back to the slide from before that you should remember, just displayed here very small. And if you apply these graphs to the map of Switzerland and colorize all the rivers according to their pollution with micropollutants like diclofenac, we can see the following. The concentration of micropollutants in the blue marked rivers are under the threshold of 0.05 for diclofenac. And with the implementation of the water protection law from 2016, so that what we have been talking now, we can get the concentrations of micropollutants in the yellow rivers with a share of at least 2% treated wastewater below this threshold. So we can solve this by the implementation of the law that we did in 2016. But there remain the purple rivers, and that will still exceed the threshold even after implementation of the upgrade. In numbers, all in all, we have about 5,000 kilometers of rivers with treated wastewater in Switzerland. 1,300 are covered with the wastewater treatment plant upgrade from 2016, and there's 1,700 kilometers remaining where we expect exceedances of the threshold. So there is still demand for action. This is actually a very recent study that I just showed, and this is the basis for a further tightening for the Water Protection Act. Because since 2020, we are working on a law claim that says all wastewater treatment plants whose discharges result in limit values being exceeded must implement measures to eliminate micropollutants. So does this mean we have to go back to start? Somehow, yes, but we are not totally new at the start because we already have a lot of knowledge and success in our backpack. To sum up, what has helped us getting here where we are now? For sure, it was a strong collaboration among researchers, regulators, and practitioners. The financial planning was accepted by all, mostly because the financial risk was not to be carried by the operators. Also, we learned that the measurement of the 12 leading substances to evaluate treatment has proven very efficient. And all in all, there was a big willingness to proactively invest towards a clean and a more sustainable environment. And last but least, the Swiss Water Association here, VSA platform, supports all stakeholders involved, and we were an important link to get the knowledge from research into practice. However, of course, there were and still are some boundaries. We still have knowledge gaps, like remaining uncertainties, therefore the research is still ongoing. Also, we reflect about our priorities and think about taking care of the bad water quality regarding conventional parameters like nitrogen. Also because for micropollutant removal, a well-performing wastewater treatment plant for these conventional parameters is absolutely necessary. And then there's always the question if we should rather spend the money on something else. But do you see there's tiny little dots here in the river of Rhine? They are not the micropollutants, but the people swimming in the Rhine River in Basel. And I can just talk about myself as potentially one of these tiny dots, that this is definitely a success story that we did, like not just the last years, but the last decades. And this was absolutely worth the money and the effort. And of course, this is now ready to be copied elsewhere. I'm therefore happy to answer your questions now, or feel free to visit our website where you can find a lot of useful information about elimination of micropollutants, like datasheet, technical recommendations, and I strongly recommend to take advantage of these experiences when implementing similar legislation or projects. Thanks and good luck.
Thank you very much, Simon. By 2039 and 2049, respectively, member states will have to ensure the application of tertiary and quaternary treatment, which consists of removal of all these micropollutants, in a large plants, 150,000 population equivalent and above. And thank you for bringing back that we need really to think how to link all this treatment with river basin. And as Alenka was saying before, we need really to conserve good ecological status. So it's over to you.
Thank you. We are fortunate to have with us today Mr. Erwin Moetz, who is bringing over 4 decades of experience in water and wastewater industry. He significantly contributed to numerous global projects that blend technical innovations with environmental sustainability. He is an advocate of WABEC's mission, Cleaner Solutions for a Greener World. He has been involved in transformative initiatives that benefit local communities and future generations. Great to have you, Mr. Moetz. Please.
Thank you very much for the warm welcome. Good afternoon, ladies and gentlemen. I like the next few minutes bring you through a little bit about our initiatives, what we're doing in water reuse. I like to start who we are. Maybe not everybody of you knows us. WABAG is a pure water service provider. We are this year 100 years old, and we are present in the 4 different continents, and we are having our own technologies. We are multinational on 4 continents in 25 countries, and we are providing solutions focusing on conservation, optimization, recycling, reuse. We call it the reclamation of water, to address all the challenges what we have in our world at the moment. For this, we have different technologies for all kind of applications, for water treatment, for drinking water, industrial water, also desalination, and what is the topic for today, water reclamation. Also on the wastewater side for municipal, industrial applications, and sludge treatment, and also industrial water recycling and reclamation. If we look a little bit what we're speaking about, we have a lot of water on our planet, but only 3% of it is fresh water. The rest is captured in oceans and salty water. Out of this 3%, almost 2/3 are captured in glaciers and ice caps on the poles. So only a tiny fraction of 1% we can use directly without huge investments or huge energy, like for desalination, which is highly costly and needs a lot of high technology to do it. Out of this 1%, almost 1/3 is in groundwater, and it's in some areas are not really easy accessible. So we speak about 0.4%, which is on surface water, which we can easily access. 2/3 are in lakes, some is in the soil. So what we can use is in lakes and rivers, and sometimes also some part of the atmospheric water. So we are speaking really about a tiny fraction of all water what we have. Therefore, it's so important that we take care of our water and we use it more than one time, and reuse is really a big challenge. Yeah. Meanwhile, many people are sacrificing water scarcity, not only in standard countries where we know in the desert, in the Middle East or in the Sahara area. Even in the last years, we find this problem also in Europe, especially in Southwest Europe and in the South Europe states. And therefore, water reuse is from great importance. And also, what is the topic from me today? 70% of the fresh water is used in agriculture. So here we have a big potential for reused water in agriculture and the irrigation side. So what we can do, we can employ the latest technologies what are available to us to turn fresh water or to turn wastewater again in high quality water that we can reuse it. And especially the reuse where it's very easy to be done is in irrigation or in agriculture, because there is not such a high quality like for potable water necessary. And the production of such water is cheaper than drinking water itself. If we speak about reuse, then we have to think also that 80% of the wastewater worldwide is not treated at all at the moment, and is discharged in lakes and rivers without any treatment. So what we can do to use the latest technology to produce water for irrigation, for urban service water, for example, for firefighting water, and and landscaping also, or even if the cities have already a two-way system that we can use water for toilet flushing instead of use drinking water for these kind of things, or then to turn wastewater again to potable water. Here we have two different possibilities: indirect potable water and direct potable water. And of course also for industry, which is also using a lot of water. In Europe, if we go a little bit more to the topic here, we are facing recently more problems with droughts and scarcity. And only a small fraction, as you can see here, is reused. From 40,000 million cubic meters on wastewater which is produced in the European Union, only 3% is treated and reused. By 2030, this problem will increase, and most probably some studies say will affect half of the population of Europe, and therefore it's very important that we do here something on the reuse side. Especially municipal wastewater is very easy to treat and can very easily reused in irrigation wastewater. What is the regulation? What we have now on the European side? European Union released this water reuse regulation in the year 2020, and this has to be implemented by the member states until 2023. Some of the states did not follow this regulation up to now. 1, 2, 3. This I wanted to show. Here on this slide, we have some states in Europe which are already quite advanced, like Italy, Spain, Malta, and Cyprus, with a high degree of reused water. The green states here on this map, they implemented the EU regulation from 2020 for reuse. So they are obliged to take a minimum of reused wastewater for agriculture and irrigation purposes. The purple countries, they took the opt-out version. They will have opt-out for 6 years. They can join this regulation 6 years later. So how we are here in Romania with this regulation. The regulation was going through the parliament in December 23. For the moment, we are missing the methodology, how we can implement and how we have to implement this regulation. Romania is producing around 5 million cubic meter wastewater every day. And this wastewater is treated in more than 600 plants. Better or not so good, we see on the rivers what we have in Romania. Some are a little bit more black than other ones. Some jokes is that the Black Sea is called Black Sea because of the wastewater which is going inside. Which technologies we have? Technologies are available, different technologies for different applications. In general, multi-barrier systems, advanced multi-barrier systems, what we can apply for drinking water, direct drinking water or indirect, where the water is going first in a natural basin for further treatment, or industrial water. And what we're speaking today for urban water or irrigational water, here additional treatment step with a filtration system and a disinfection system is used. So coming to our case study from Madinati. Madinati is a city east of Cairo. It's a city direct from the drawing board. It's not a grown city. It spans over at the end when it's finally built up 100% over 32 square kilometers, and will inhabit 600,000 people with a lot of green spaces between the house units. This is a unique plan, especially in the Cairo area. There are not too many green spaces, and yeah, will provide 120,000 housing units for approximately 600,000 people on the east side of Cairo, close to New Cairo, which was also built recently. The Madinati was planned and financed by Egyptian visionary Mr. Talat Mustafa with his group and some additional sponsors from the Middle East. It's the first city which is privately founded in the area, and also the wastewater treatment plant is fully private founded. And it's designed to build in stages because the city is growing slowly. So the wastewater treatment plant is growing with the needs of the city. At the moment, there are 2 stages out of 4 finalized. Stage 1 went in operation 2018 and stage 2 2022. Both stages were built by WABAG in a DBO or EP plus O&M. So we are also operating the plant since that time. And the water which is produced here in the wastewater treatment plant is 100% reused for the irrigation in Madinati city to water the green spaces between the houses. Each stage of this plant is designed for 40,000 cubic meters per day. It's a standard wastewater treatment for the beginning with additional treatment steps at the end of the treatment with a rapid sand filter filtration and chlorination disinfection to use it direct for the irrigation purpose. The dewatering is of the produced sludge. Of course, we have also sludge there, as in every wastewater treatment plant. The sludge is first in aerobic digesters neutralized, and afterwards with centrifuges dewatered. And here we have a scheme of the treatment process. As you can see, from 1 to the step 5, this is a standard treatment process with primary clarification, biologic treatment, secondary clarification. And at stage number 6, we have the sand filtration, and at stage number 7, the chlorination, and then it's going direct in the pipeline for the irrigation purpose. The similar thing is on the sludge line. The sludge is digested in anaerobic digestion and then dewatered with a centrifuge. And at the moment, the sludge is disposed, but it could be used in agriculture as a fertilizer. Here some values about the water quality. If you see here, the BOD, COD values are very low. For example, in Romania, discharge value for COD is 125 milligram per liter. And here we have less than 50 milligram per liter. And also the coliform bacteria, which of course you don't want to have in the water for the irrigation, is reduced to 2.2 bacteria per 100 milliliter, which is a very low value. We received for this plant a big award from Global Energy Award because Also, the biogas produced in the digesters is used to produce energy to run the plant. It's not 100% attack because the sludge is not sufficient to produce 100% of the necessary energy, but more than half of the energy is produced by the plant itself. And Advantage Austria handed over this award to our Egyptian colleagues last year in 2023. We have then some other examples of reuse plants, mainly for irrigation and agriculture, but also for industrial reuse, which are already implemented and which are working worldwide. At the end of my presentation, some awards what we get from international publication like the GWI for our initiatives in water reuse and our water reuse technologies. This was from my side. Thank you very much for your attention, and have a nice afternoon.
Thank you very much, Mr. Erwin. Due to time constraints, you presented only this water use you were asked, but it's really important to know that behind this, Madinati means my city in Arabic language, which means that it's an urban planning department thinking not only about water use, but how to coordinate all elements that urban cities ask and all needs it has. And one of the needs was on urban irrigation, and they have the greenest part I've ever seen in Egypt. Thank you. It's over to you.
Thank you. We are fortunate to have today with us online, I guess, Engineer Luca Siglia, who currently is working as the project officer at the EU Commission's Joint Research Center in Seville, focusing on the circular economy of solid waste and sewage sludge. Previously, at the Technical University of Vienna and the City of Vienna's Waste Management Department, he worked on sewage sludge management and phosphorus recovery from sewage sludge ashes. So, Igle?
Thank you for having me. I hope you can hear me well. So I will share my screen with you. Yeah.
Please do.
Just a second. My presentation. So, can you see my presentation now?
Yes.
Okay, thank you very much for having me today in your conference. Very nice. And best wishes from hot Seville. So we are already reaching 40 degrees and I'm sweating in my office, but I try my best to do the presentation. So what I want to present to you is our feasibility study, which we did at the GRC last year to support the policy developments of the current sewage sludge directive. And it was a work between GRC Seville and GRC ISPA that supported us in our work. Quickly go through the agenda. So what I will present, have a very brief overview about the sewage sludge directive, which is already very old, from the 1986 years. There was a sewage sludge directive evaluation last year done by DG Environment, and we will present, or I will present quickly the possible ways forward from our study and draw some conclusions for our discussion afterwards. So the sewage sludge directive was created 1986 to correctly use the sewage sludge in agriculture and also to contribute to resource efficiency. That means how the nutrients that are within the sludge, like nitrogen, phosphorus, but also the organic matter, can be used efficiently. But it was also a purpose to regulate the application of sewage sludge to prevent any harmful effects on the environment, on human health, vegetation, and so on. So this was done mainly by introducing limit values for heavy metals, 7 by number: cadmium, chromium, copper, nickel, lead, and zinc, and mercury. So they had limit values for the sludge which is applicated, but also for the soil on which the sludge should be used. But what I want to mention already now is that the member states that applied the regulation already implemented more stringent values especially on these heavy metals, but also implemented already additional parameters, like, for example, on organic substances, organic pollutants, such as dioxins, furans, but also PCBs or whatsoever. But what we also see that in the last 40 years, many things have changed. And I think we have a better knowledge now and a better understanding on what is in the sewage sludge and what could happen if we apply sewage sludge on agricultural soil. And for this to also have a revision, a potential revision of the sewage sludge directive, an evaluation was done by our colleagues from DG Environment. And I want to really go quickly through it, have some selected points to present to you. What was their conclusion or what was their finding? So at the moment, we are applying 7 to 8 million tons of sewage sludge per year in the agriculture. And this is still one of the main routes of sewage sludge. This is quite constant over the years, but we have a high fluctuation between the member states. We have some member states having 90% of sewage sludge applied on agricultural land, and some member states only 20%. So there's not a very heterogeneous picture. But agriculture use is the cheapest way for sludge disposal, still is, and this is beneficial for the operators of the treatment plant and for sure for the farmers, because they get a very cheap nutrient source in comparison, for example, to mineral fertilizer. What they also saw in the study or in the evaluation, there's a decreasing level of heavy metals in the sewage sludge since the implementation of the sludge directive. The question is this coming from the direction itself or for some other regulation that came into place, like, for example, the indirect discharge regulation or bans on specific metals, like, for example, amalgam at dentist bureaus. So there were some regulations in place that could affect the heavy metals or other substances in the sewage sludge. And what I already mentioned before, in the meantime, member states already adopted more stringent requirements to have a more environmental protection in their countries. But what they also found in their study that we have limited information. So what is the link between agricultural soil quality and the application of sewage sludge? So there's really a lack of information because it's sometimes not clear, is, for example, a higher level of heavy metals a result of the applied sewage sludge? Or do we have some other effects coming from deposition, coming from other fertilizers, manure, or whatsoever? So there's a missing information, definitely. And also the policy frameworks have evolved considerably over the last recent years. So we have the Green Deal to promote recycling, promote recovery. We have zero pollution action plans. We have adapted lists also on critical raw materials, for example, to promote the recovery of phosphorus and valuable nutrients even more. And I want to come to the presentation of our feasibility study. So what was the objective? We want to bring forward some preliminary assessment of different policy options for a possible potential review of the sewage sludge directive in the future. What did we do? We developed a baseline scenario for the year 2050 and developed 2 policy options. And we go into detail on the next slide. And I want to focus here already that phosphorus is, when we talk about sewage sludge and recycling, phosphorus is the most valuable and critical nutrient. So we see it also on the list for the critical raw materials. We also have the organic matter and nitrogen, but they are less important when we talk about the recycling of sewage sludge. This is why we focus on the phosphorus in the upcoming presentation. The parameters we had a look at, we had some quantitative parameters, but also some qualitative. We looked at the effects on human health, environmental protection, some gases emissions as well, like methane, the nutrient recycling potential, what are the costs of certain policy options, the benefits, how could we stimulate also innovation, what are also the social impacts, for example, on job creation, and also the competitiveness of the European Union and innovation incentives. And when we talk about the objectives, it's always very important, the objective A, to have this environmental and health protection when we spread the sewage sludge on agricultural lands, and then also be in line with the objective B, to be in line with the current circular economy principles, but also zero pollution. So we were looking at the different scenarios. On the one hand, there could be a possibility to monitor the sewage sludge quality, control it, and then apply more sewage sludge on agricultural lands. Or there could be an option to ban sewage sludge for recycling, so the direct application of sewage sludge for recycling, unless we have a specific treatment. In the last years, new technology arose. For example, the sewage sludge is incinerated, and then from the sewage sludge ash, you can produce already fertilizing products which have total different characteristics in the sense of the quality, removal of pollutants, and the availability for the plants. So what we did, we targeted these phosphorus recovery goals on different sizes of wastewater treatment plant. So if we had a look, for example, if we would implement it at wastewater treatment plants greater 20,000, greater 50,000, greater 100,000, and greater 500,000 population equivalents, to have also a certain sensitivity analysis and see also the effects, depending on what size we consider in our study, what would be the effects on the parameters I discussed before. So what you see, we have then the baseline scenario, so the development until 2050. We have the policy option 1. So we want to really more monitor the quality of the sewage sludge and control, so that only sewage sludge is applied that fulfills the requirements of the directive, current directive. We set it a minimum target to recover at least 75 of the phosphorus in the sludge if they, for example, exceed a certain size. And in the policy option 2, we really have a ban more or less of direct sewage sludge application, and the wastewater treatment plants have to produce from the sewage sludge a EU fertilizer product. So first incinerate and then apply a new technology to recover the phosphorus. And about the methodology, so for the baseline, we had a look at the demographic evolution. We also took into account national legal frameworks on sewage sludge in the different member states, and also the expected evolution of other legislation coming up, like, for example, the Urban Wastewater Treatment Directive, Landfill Directive, and also other strategies. And what you can see about this is the basis for our work. What we've done, we rerouted the sewage sludge in the different policy options. What you can see on the policy option 1, for example, if there's already a mono incineration, this is going to 100% of mono incineration with peer recovery. Also, sludge that is currently co-incinerated will go for mono incineration and peer recovery. And for example, when it's currently land spreads, we considered that some sludges have a good quality. Or most of the sludge has good quality, so 90% could go to agriculture, forestry, or landscaping. But there could be countries where only 60% is good quality or 30% good quality. So we also made a sensitivity analysis within the policy option. And the other part, which is, for example, a bad quality of sewage sludge, is then going for mono incineration with peer recovery. And for the policy option 2, mainly all of the sludge that is currently used otherwise, like co-incineration, land spread or landfilling or other, is going to a mono incineration, meaning you only incinerate the sludge without any other wastes, and then go for a technical phosphorus recovery. And I directly want to jump to the results we are having. And this is quite interesting for me to show you the baseline scenario, but also situation 2019. So we have here the distribution of sludge management options in the different member states. We have here, for example, Belgium 2019, and then the baseline scenario 2050. In green, you have always the sludge application for recycling. The darker green is the composting. Orange, the co-incineration. Some countries have already a mono incineration. This is red. Landfilling is gray, and some other application, which is sometimes not very clear. And for example, you can see that just by applying the landfill directive, you have already a great shift of sewage sludge from landfills, maybe to agricultural land or to composting, without doing anything, without any policy options. Then with arising technologies to recover phosphorus from the sewage sludge ash, we assumed here that the sewage sludge that is already mono incinerated will also go for a technical phosphorus recycling to produce a fertilizing product. And then you have already some member states in place, like for example, Germany and Austria. They already have some legislation that you have to incinerate the sewage sludge from a certain wastewater treatment plant size and go for a technical peer recovery. That would result that already, for example, here in Germany, 70% of the sewage sludge will be mono incinerated, and then you have a new fertilizing product. And same is then more or less valid for Austria. And when we look at the different policy options, when we talk about sewage sludge management options, one of the main findings for us is when we talk about mandatory peer recovery from wastewater treatment plants, we see that this could be a sound assumption that the sewage sludge from wastewater treatment plants greater 50,000 population equivalent could be going, or should be considered, because with this 50,000 K, we cover 70% of the wastewater that is occurring in the EU27. but we only address 12% of the wastewater treatment plants. So you have a great amount of wastewater or phosphorus you're considering, but the regulation or the policy options applies only about for 10% of the wastewater treatment plant, and is also for sure affecting the cost and whatsoever. So in the upcoming slides, I always want to present here the results for the wastewater treatment plants greater than 50,000 population equivalents. And what we see here with regarding the sewage sludge management options, we see here for the policy option 1, we have a higher rate of direct agricultural sewage sludge application. This is quite clear compared to policy option 2, because in policy option 2, we go for the incineration route with technical peer recovery, and also quite obvious with the policy option 2, you go for more mono incineration and with the targeted phosphorus recovery. And we see now on the next slide the effects, for example, on the peer recycling, but also the environmental effects. In general, we see with this mandatory recycling rates, for sure, more phosphorus will be applied to agricultural lands, both at the same order of magnitude for both policy options. We see for the policy option 2, we have a slightly lower amount of phosphorus recovered compared to policy option 1. This is mainly due to the fact that if you incinerate a sewage sludge and then apply a technical recovery unit, you always lose, for example, 20% of the phosphorus just for the sake of technology, because you never can recycle 100%. But a big advantage is here, we also expressed here the agronomic P efficiency. So the efficiency of the fertilizers that are produced from phosphorus recycling technologies is always higher compared to a normal sewage sludge, because you have some technical chemical processes and you can enhance the availability for the plant. What we also see is the phosphorus is cleaner in the policy option 2, because all the organics, dioxins, furanes, other polyhydrocarbons will be destroyed with incineration. And you can also remove heavy metals to a great extent, sometimes 90–95% from the sewage sludge, and the recovered material is very clean compared to a pure sewage sludge applied to agricultural land. But we have here the trade-off, as I already mentioned before. If we have more incineration, we lose carbon and the nitrogen. We transfer it to the gaseous phase, and this will be lost for recycling in the European Union. But more critical, I want to remember that, is the phosphorus when we talk about the sewage sludge. When we talk about the methane emissions, so the reduction of methane emissions is similar for both policy options. This is mainly the reduction because we distribute with a different distribution, because we avoid the landfilling. So already the methane emissions from sewage sludge in general in the European Commission is low from the landfills, but bringing less sewage sludge due to different policy options, we have an additional decrease of methane emissions by avoidance of bringing sewage sludge to the landfills, which is also good for the climate. For sure, if we, for example, have this mandatory phosphorus recycling and these new routes with these new policy options, we need new installations. What we already see in both scenarios, so in both policy options, we have already some countries that will implement the phosphorus recovery and mono incineration have already mandatory P recycling targets, meaning we will have already at the increase of, we see here in dark blue, of mono incineration plants, but also P recovery units. So also already in the baseline scenario, but with implementing a mandatory technical phosphorus recovery for the wastewater treatment plants greater than 50,000, for example, in policy option 2, we will need 115 to 230 additional mono incinerators in whole EU 27, and about 40 to 90 new phosphorus recovery plants, which are normally installed directly at the incinerator or at the central point of the country. So there will be some significant installations, new installations for burning the sludge, but then also for the recovery of the phosphorus. And for sure, more for policy option 2 than for policy option 1. This comes always with higher investment costs. And what you see here is the investment costs in million euro in total. So we didn't consider, this is not the cost for the sludge per euro per ton dry matter. This is really the total investment costs. And we didn't consider any reinvestment costs here. So only what would be the costs if we have the new plants, incinerators, but in the new technical phosphorus recycling. And if we have the policy option 1, we talk about with a very high uncertainty because we expanded the methodology. So sometimes 30% of agricultural sludge can be used still in agriculture due to quality, and sometimes you have to incinerate more. So we have here a very high bandwidth of potential total investment costs, but with that, there would be in the range of 2,500 million euros to 5,400 million euros for policy option 1. But if we go for a technical way, we ban sewage sludge application on agricultural land, the investment costs will be more or less double. So this is then really the total cost. Thank you for the time. I will consider. I'm coming to the end with the last slide of the costs and then the conclusions. So when we talk about costs, we already have a small increase of the costs per euro per ton dry matter of sewage sludge in the baseline scenario. But if you apply policy option 1, the cost will increase by about 50–60%. And if you go for a technical solution, the costs per ton dry matter will increase by 100%. Having, for example, then only 26% more phosphorus applied to land or 50% with policy option 2. So also the cost per ton phosphorus will increase significantly. And we also had a look not only on the quantitative parameters, but also on some qualitative parameters. When we look, for example, on the environment and health, what is improvement, for example, on contamination? As I discussed before, we have strong improvements for policy option 2 because we incinerate, destroy organics. Nutrient loss, we bring very good nutrients with a higher plant availability back to the agricultural land with policy option 2. But we will lose nitrogen and carbon with policy option 2 with this incineration path. But we also have the possibility with the second policy option with some recycling technologies to also recover some, for example, iron, aluminum, calcium. So we have some other elements potentially recycled. And this is a great improvement. If we produce, for example, an ash, this can be shipped from countries with a low demand of nutrients, for example, Netherlands or Belgium, whatsoever, to other countries which have a need on, for example, phosphorus in their country. And, for example, we strengthen the competitiveness in the innovation if we apply new technologies. And also, we create new jobs by having new technologies, for example, incineration and recovery. Last slide, the conclusions. So already without the sewage sludge specific legislation, there will be already a huge change in the sludge management within the EU. We see with terms to environmental and health impacts, the policy option 2 performs better because we remove organic compounds. Then we have also a targeted removal of heavy metals. With policy option 2, we can also reduce additional contaminants, but we can also recover further elements, like discussed before. But this really comes with the trade-off of higher price and the loss of nitrogen and organic matter. Policy option 2, we have an overall small, lower amount of P recovered due to the technical processes, but the phosphorus is then more available to plants in the short term. But also we can use it, or we can apply it more in a controlled way. And also we can transport it to other countries where it's really needed. But with the higher ambition of this technical approach with policy option 2, we have sensitively higher investment costs and operational costs, almost by the factor of 2. But what we could have, for example, if we don't have policy option 1, with all the monitoring and control of the sludge quality, the administrative costs will be lower for policy option 2. So this was a very quick overview about our studies, and I'm very happy to discuss our results with you in the discussion panel. Thanks a lot.
Thank you very much, Dr. Lucas, coming bold on supporting future policy development of the end products, sewage sludge. Ilse?
So we came to the question and answer session. So if one of you wants to go like deeper in the presenters, so you can ask your questions. Yeah.
Thank you very much. I would have questions for the first session. I would say that for the first, among the first presenters to Mrs. Shakiri, if I can. I mean, I see that from the climate change perspective and also for coping with the climate impact. And this is really a huge work that you are you have been done so far and you still have, you know, in the coming future to do. If I understand well from your presentation that actually that you have as the commitment as a huge reconstruction program based on the infiltration study that you have done. Actually, I'm just wondering, and this is from our experiences, that's also what we could see, that when you are getting into the change to the urban environment, especially for replacement of the, I would say, the aged pipes, you are putting our impact into the urban hydrological cycle. I'm just wondering whether when you had this kind of reconstruction plans, was there any impact study on the urban hydrological consequences of all of these? Because from this kind of infiltration study, you can have a very good insight how much water is entering to the sewer system from the groundwater, from some other sources, how much is the black connection. So indeed, it could have an impact in general also, not just in Skopje, but in rising the groundwater level in certain areas, which is impacting other things, but also on the rainwater impact, so that what is not entering to the wastewater treatment plant and not entering in the sewer system, well, it gets to somewhere, so most likely on the streets and so on. So it means that there is an increased maybe need for other storage capacities and for other facilities. So it's kind of interesting from our perspective that whether this kind of aspect has been studied, because we had some experience from smaller cities, and we see that there was an upcoming other actions that they needed to scope with in the future. Thank you.
So if I understand the question, the question is whether we are planning to have another storage for stormwater or something like this. Okay, I will try. So first of all, we did the inflow infiltration study, which is, how to say, crucial for well capaciting of the wastewater treatment plant, in order not to oversize it or not to have lower capacity. So we did it. So it was, as I mentioned, 1 year's study, and it was something like requirements from the banks, from EBRD as a bank, for a loaning. And they said, the point is that the banks want sustainable company which will run the wastewater treatment plant, since we have yellow FIDIC DB, so design and build, and the operation will be under City of Skopje or the public enterprise. So in order to have sustainable equipment plant, and in order to have a sustainable company which will cover the cost of the wastewater, which will be able to cover the cost, we have to design approximately accurate figures in a way of construction. So that's why we did it. And a part of inflow infiltration, there was a FOPIP as well, financial operation program in the implementing in the company. We, during the implementation of the inflow infiltration study and during the performance, so one company, I don't want to mention which is it, but they did really, there was a tendering and everything. So they did really amazing job. So we were very surprised of all the figures that we gathered. So after that, we received reports. So there is midterm objectives. There were long-term objectives and short-term objectives. So we will implement the short-term objectives, but there is a lot of money demanding. So we have to work on, we have to focus on several areas which will be recovered. But we are not going to split the system on storm and sewage water, but because we already have combined system, we are building the new collectors, so not to lose money. So we will work only on recovering of the system.
I'm not sure if Mr. Dr. Lucas is online. He is okay. So my question would be like this, as probably you know, the incinerators at the wastewater treatment plants were highly advertised and promoted to be implemented in many countries in Europe. Of course, nobody told us how expensive it's to run these facilities, incinerator facilities, and which is the impact on the environment of running these facilities, and also the investments are high in these incinerators. But did you take in account that we are talking about reducing the impact on climate change and on the environment from what's happening in a wastewater treatment plant? Did you take in account that this phosphorus recovery or reduction of the methane which is obtained by using gas in the incinerators, which is the lowest impact on the environment and the climate change, because burning gas and making really high investments in these facilities, I don't know if you balanced this when you looked at the options that you were presenting.
This is true. We didn't do an LCA on the whole scenario. But what we know from sludge incinerators, for example, I mean, they normally need initially gas to start the process. But we also know from many other cities, also from Switzerland, Austria, and Germany, that if you operate a sewage sludge incinerator with a pre-treatment of the sludge, for example, with dewatering and pre-drying, that needs additional need of energy, or say, let's say on the other way, you have a positive balance on the energy. So the gas you need for incineration will be substituted by the additional energy you get, for example, electricity, but also heat from the burning of the sludge. So you have some positive effects on the environment on that. We have some other potential negative effects, for example, when it comes to the LUF gas, N2O emissions. We see that, for example, when burning sewage sludge, there could be some additional emissions on these gases. They also have an impact on climate change, definitely. But if you operate, for example, an incinerator properly, you can also avoid these gases emissions. But for example, in comparison to avoid the uncontrolled methane emissions from a landfill, there's not now scientific proof comment from my side, then it would be better to incinerate it instead of letting a landfill and produce methane emissions over the centuries.
Thank you. Over to you, gentlemen.
Hi there. My name is Ionuț Procop from GWP Romania. I have a question for Alenka Mobi-Zalaznic about sustainable water solutions. So I had some information that nature-based solutions and sustainable water retention solutions can actually be the key to reverse climate change. So I would like to have her view on this. And a second question would be that on one of our slides, to treat the water, it came up about 0.63 euros per cubic meter. So I would be curious as if this treating the water by using natural, let's say, building areas, how does it compare? Is it cost effective? And what is the proportion of the impact on the nature? Because I think you cannot treat all the waters. I know plants that can digest nutrients and heavy metals. However, to what extent can this happen? Thank you.
Thank you for the questions. In terms of climate change mitigation, we rather calculate the climate change adaptation. I'm not sure that the entire mitigation process can be reversed in the nature-based solution because they are really area-intensive technology. So what we do is sometimes at some projects calculate the adaptation focus. I didn't understand the question on cost efficiency. Not all. Can you repeat the question on efficiency?
Compare with technology being implemented.
So the cost of wastewater nature-based solutions and
Correct.
yeah. The investment costs could be because of the area intensity. The really investment cost can be quite comparable. But the operating cost is a winning side of nature-based solutions, and additionally also the resource efficiency. So this is the extra to it.
To sum it up, just as we are captivated by the film industry, Academy of Words, known as Oscar, during this very session, we have had our Oscars in the form of Circular Water Globe Awards. Please join me in giving a round of applause to our excellent presenters today, Anna, Linda, Alenka, Simon, Erwin, Lucas, and Elsa. Thank you.